Know the announcements. Contest ends at 4, closing ceremonies at 5. Fail of things in the chill out room, intro to lockpicking in the lockpicking room. We have one more talk after this, and then we have an after party at the 23B shop. So come to closing if you want all the rest of the wrap-up details. Other than that, we still have shirts for sale out in the registration area for $20. We also have the talks available outside at the media archives table. $5 for an individual talk, $40 for the whole con. You get it on this very fancy LayerOne branded thumb drive. Coming up next is David Sharpe with Intrusion Hunting for the Masses. So give him a big round of applause.
How's the sound? Can you hear me? How about that? Is that any better? Now? How about that? Video, are you ready? Okay. Good afternoon. Thanks to LayerOne for having me, and thanks to all of you for coming. This talk is Intrusion Hunting for the Masses, a practical guide. Please note that I'll provide an email address at the end if you want a copy of these slides. There's a lot of technical detail in this material. Please don't feel rushed to try to scribble down everything. Just email me for the slides and I'll reply back, likely later tonight. First, a disclaimer. Opinions expressed in this presentation are my own. I'm speaking for myself, not for GE, nor not anyone or anything else. I am David Sharpe. I started off in IT and systems programming about 20 years ago, and I've worked in a variety of roles over the years. I've spent the last 10 years focused more on IT security. For the past 4 years or so, I've worked for GE CERT. Why am I here? I believe that we are finding fewer and fewer high-end APT intrusions across the board. To be clear, I am talking about the private sector, not the military or intelligence services spaces. I believe this general downward trend in detections is spread across all industries and is worldwide. I am not saying that there are fewer high-end intrusions. I'm saying that we seem to be finding a much smaller percentage of them compared to just a few years ago. Why the drop-off? Have attackers lost interest? In my experience, that's a no. Are we generally all better defended? Are our systems becoming impossible to breach? I think that is a no. Harder to breach, yes. Impossible, no. Have we become less effective at finding intrusions? Maybe. For the sake of discussion, let's pretend that there are 5 skill levels of targeted attackers, assigned school letter grades ranging from A through F. Hacking RSA to abuse tokens to enter a target, A game. Stuxnet, A game. Using exploitation, C2, lateral movement, and exfil techniques from 5 years ago, B game. Spearphishing the same way that you have for the past 10 years, F game. Frankly, we all struggle with finding PhD level attackers bringing their A game. Many of us struggle with attackers at the B or C skill level. Many have success finding attackers using D or F game tactics, but is that good enough? What's wrong? This way? Maybe I'll just move over. I think there's been a general upward trend on well, never mind. The purpose of this talk is to share several simple and easy to do, yet effective techniques to find intrusions at all those levels, from sophisticated A through to humble F. If you take some of these ideas back to your own organizations, a significant percentage of you will find intrusions when you return home. So what's working for finding intrusions these days? That, in my view, breaks down to 2 broad buckets of activity. First, alerts from known bad things, indicators, generated mostly from automated network or host detection systems. There's about a 50-50 split in the success rate between network and host-based detection, at least from what I've seen working for finding intrusions for the past few years. The balance may shift more to the host detection side as more gets moved to cloud environments over time. Automated detection is still effective and essential, but isn't what we're covering here today. Another approach to finding intrusion is by hunting or manually looking for signs of possible badness across broad data sets. This will be the focus of this talk. Now, manual intrusion can and should, where possible, lead to new forms of automated detection. Data stacking, a term I first learned from a Mandian presentation, is another key to success with intrusion hunting. Data stacking basically refers to ways to massage a data set to get the abnormal and interesting things to bubble out of the normal data. The concept of data stacking will make intuitive sense as we work through the practical examples in this talk. So what about data science? You hear a lot about that. Where does that fit in? Data science is great for a broad spectrum of problem domains. Data science techniques can certainly help better inform better detection and hunting techniques. However, in my opinion, the simple element of time is, in many cases, the most sophisticated data science model element that pays off for much of a search problem set. Not high-end math, not complex statistical techniques. Time, just a simple correlation between two or more related events is often enough. Think about the hammer toss malware from last year, where you needed to see the first C2 action to rogue accounts on Twitter, followed by activity to certain subdomains on GitHub, all within a certain amount of time. I also don't hunt using complex virtual visualizations or graphing. Visualizations certainly have their place in many problem domains, but I haven't found a way to get a graph of some enormous data set to help me spot an intrusion. We're aiming for simple but effective. So what does work? First, know thy data. Know what data is available on the systems you are collecting from and what you can derive from what is present or happening on those systems. Know what each element or field in the data truly means. Second thing, and this is a big deal, know what all forms of badness look like and check for signs of that in your data set. Be a student of intrusions, both yours and everyone else's. Have an unrivaled knowledge of your search intrusion and incident history as far back as your records go. Read vendor reports of how APT actors operate and how specific intrusions played out. Read court indictment papers for people charged with hacking. Be an omnivore and study everything you can get your hands on to broaden your knowledge of how real-world intrusions play out. Now, if you're wondering what the blue arrow is all about, I use a blue arrow theme in these slides. The way I see things, we all get arrows fired at us on a regular basis by attackers. This talk's purpose is to give you some arrows for your own quiver to fire back, to help better defend yourselves. We will cover 12 practical examples of hunting in this talk. These 12 ideas were purposefully selected to maximize your chances of finding intrusions for all intruder skill levels, A through F, so that you can help reduce damage to your organizations and customers, raise your adversary's cost of operating, and hopefully help you find something quickly to show the value of your hunt function, a quick win. Let's get started. First, shim cache and AM cache. If you act on only one thing from this talk, this is it. What is shim cache and why is it valuable? Basically, shim cache is bookkeeping data that Windows automatically maintains to support application compatibility. Shim cache is used in Windows XP through Windows 7 on the client side, and from Server 2003 through Server 2008 on the server side. As a side effect, shim cache gives us a record of what processes have been run on Windows systems for a time span that could potentially span back months or years, depending on the age of the system and how it is used. If an intrusion happened 2 days ago, 2 months ago, or 2 years ago, this might be your best shot at seeing that. A convenient and easy one-stop shop to see much of what has been ran on the system over an extended period of time. Many intruders of all skill levels, including some of the best attack teams in the world, still don't clean up shim cache or AM cache, despite their being meticulous about cleaning up otherwise. How can you get shim cache data flowing back for analysis? You can either run this Python script from Mandiant directly, the link is on screen, if you have a suitable Python runtime available across all your Windows platforms. Or you can make a Windows exe out of the provided Python script using something like py2exe and deploy that out. If you pull the resulting data back to a central system for processing, you're looking at about 100 KB per machine. You should aim to collect and analyze shim cache or AM cache from all of your Windows endpoints, both client and server. But servers are the sweet spot. Why? Servers, in my experience, remain the #1 initial entry point for breaches, especially internet-facing servers or other servers in DMZs. Windows clients are also important due to the prevalence of targeted watering hole attacks in recent years, and to a lesser extent, targeted spear phishing. On modern Windows OS versions, shim cache can be anywhere from a few hundred entries long on a brand new or lightly used machine to 1,024 entries on a typical production machine. Shim cache records look like what's on screen. Shim cache records break down as follows. The first field is the last modified timestamp. This is not when the process last ran. It is the last modified timestamp from the file's MFT entry on the file system. For newly dropped malware that has not been time-stopped, this field is useful. If it is time-stopped, then at least you know something ran, maybe not necessarily when it ran. Next, the last update field was only used on Windows XP. That was more useful for telling when something last ran. That field isn't used set on modern Windows versions. Next, the full path field shows the location of the binary on the file system, so this is definitely a good one for our purposes. The file size field was only set on Windows XP and Server 2003, not anything newer. And the last field is the execution flag. That is a binary field set to true or false. I haven't found this field useful for hunting, so leave this one alone for now. Consider an example. Here some NTFS entries are time-stomped. These July 2010 dates made no sense given the age of the system and stood out in the data set when sorted by timestamp. Another thing that stood out as a spec were the file paths. Does anything normally run out of C:\Windows fonts? Looking across your entire shim cache and AM cache data sets, you'll see the answer is no. The last few commands by themselves could be harmless normal IT user activity, but in this context also could be scanning or recon since they are grouped so closely together in time. For your reference later, here are several links to more information about shim cache. Now, next, let's break down AM cache, shim cache's replacement. Shim cache was replaced by AM cache starting with Windows Server 2012 forward and Windows 8 forward. AM cache is still in use with Windows 10 and Server 2016. AM cache serves the same purpose as shim cache, but has several more useful fields for hunting. How do you get AM cache data flowing? The source file, amcache.hve, is locked on running machines. This registry high file is small, so an in-use copy of the AM cache high file back for offline processing should work fine. Then you can run the original author's Python script directly. The download location of the tool is on screen. With AM cache, you have more useful fields to stack and mine. A breakdown of the available AM cache fields is on screen. There are more fields in AM cache for the attacker to accidentally signal their existence. Some of these fields get set by their compiler or linker and may not be simple to fake, or might be easy to forget about. There are more fields to leave blank when they should be filled out, a lot of ways to make mistakes and give away an intruder's presence. Note the SHA-1 hash field at the bottom. That is useful to help filter legitimate binaries from the data set. Now, what should you look for in the shim cache and AM cache data? Stack this data thoroughly and see what bubbles out. Remember what I said before about attackers neglecting to clean this data up? So spending extra time here is worth the effort. In general, you're looking for any tools that support any of the key actions commonly taken across intrusions: reconnaissance, privilege escalation, credential dumping, lateral movement, data collection, archiving, exfiltration. At a minimum, check for signs of credential dumpers, sequences of recon activity, net commands, pings, use of scan tools clustered together in time. Look for archivers being ran. Command line RAR is still the big one, and look for 7-zip now too. Look for EXEs running out of abnormal locations on disk. Look for things being ran with short file names like 1.exe or w32.exe. Here's an excerpt from AM cache from a breached machine, found using the AM cache tool's timeline feature. AM cache has a -t argument that you can use to generate a timeline. I had to edit a lot of fields out of the AM cache output to fit it on the slide so that you can see an example of what malicious activity might look like in timeline form. There are normally no EXEs present or ran out of the top of C:\, users. There's normally not a file named abscan in C:\, Windows System 32 either, so that is why these records bubbled out of the data set. I strongly believe a high percentage of you will find an intrusion soon using shim cache and AM cache only. Here's some additional links for information about AM cache for your reference later. Next, the second highly effective arrow for your quiver. This might sound counterintuitive to some, but antivirus logs are still one of the most productive places to hunt for signs of intrusion that might be in progress and have been for years. In my experience, just under 20% of all targeted intrusions involving Windows systems have AV fire somewhere along the line. You are missing an opportunity if you don't mine your AV logs. That 20% figure, coupled with the fact that this type of hunting is fairly easy to do, is another one of the reasons I can confidently say that many of you will file an intrusion when you go home. If an intrusion attempt has progressed far enough along to where an AV product fires, then that is helpful. At best, you have a blocked intrusion, but you still might have an exploitable hole in there that needs to be addressed. Worst case is the intrusion is pretty far along, and AV happened to pick up just one thing in a long sequence of events. Sometimes you just get one shot at finding an intrusion, even if it has been going on for years, and this could be it. Maybe the intruder didn't follow their own best practices and make sure a newly downloaded tool or tool update was going to be missed by the target's installed AV. Trust me, mine this data, especially server AV logs, and especially for internet-facing assets. What should you be looking for? Examples include web shells. Look for any type of web shell street name and watch the file extensions. Look for AV detections where the file is under web root, under C:\Windows. Look for a detection of any kind of backdoors or intruder tools identified by your intelligence sources or experience. Look for any known bad AV street names, especially for malware types that we just discussed. Supplement that with custom HIPS detection with HIPS rules looking for how those targeted malware samples and tools work internally. If your AV product supports this in some way, even if only informational logging, look for packed executables present on servers. So, what are known bad AV street names? One example is malware that is known to be targeted from Intel collection or vendor reports. Another source might be AV detections with terms like backdoor, Trojan, shell, or web shell in the street name. In the real world, some AV vendors are better than others at naming targeted malware samples in a way that is useful for hunting and detection. I cannot name which or which. No matter what, you might want to consider supplementing your AV detections with multi-scanner solution street names for everything you find in-house. That way, if you use a vendor who doesn't name malware in a way that is easy for hunting or detection, then you can still pivot off your AV detections using one of the AV multi-scanners out there to find what every supported AV vendor calls what you found. VirusTotal is one example with API access, and there are others out there, or you could build your own in-house solution. To illustrate, you might take every AV detection that you find across your server population and submit all the hashes to a multi-AV scanner, and then hunt through the return list of street names for items that stand out. For example, you might not care about games or jokeware detected by AV on your Citrix or FileShare servers, but you might care about a detected web shell or backdoor on your database or web servers. Best practice has been for years and remains to not submit newly found targeted AP or malware samples to such public scanners because you risk leaking intel. But you should be able to safely use a multi-AV lookup for a file hash or street name over an API to see what other vendors and products call what you found internally. To help further illustrate the concept of hunting in AV logs, let's break down credential dumpers. The 5 credential dumping tools I most commonly see in targeted intrusions are WCE, PWDump, GSecDump, FGDump, and Mimikatz, in that order. I'll list some other less commonly encountered credential dumpers on screen. Find your AV vendor street names for all versions of all of these dumpers and always look for them in your AV logs. Also, if you have HIPS, host IPS, deployed, see what HIPS rules fire when these tools are ran. Hunt for those HIPS logs entries too, alongside the AV street names. Next arrow. What are you doing to find rogue network listeners across your endpoints, especially servers on the network edges? You can use regular netstat or a number of other tools. More output fields are better. Just run netstat-nabo, pull the data back, and mine it. Let's look at some possible benefits. Netstat-nabo can tell you a lot. In this example, data stacking shows more than one process name and more than one path bound to the same TCP port 1433 for Microsoft SQL Server on a single system. That is supposed to be impossible. In this case, intruder activity was being interleaved in with legitimate SQL Server traffic. Not good. Consider this. Try stacking the netstat output for all internet accessible servers by listening port and see how many ports show up just once across the entire data set. Stack output for all internet accessible servers by full path to the listening process's binary and see how many paths show up just once. Preserve all netstat output as a baseline and track all new listeners that appear over time, especially across your internet-facing systems, so that you can see what changes over time. A caveat: these are just snapshots, not real-time monitoring, so you will likely miss non-persistent listeners. For example, where a new listener spins up only temporarily based on a timer or as a result of port knocking. Next, user agent strings in HTTP traffic can be good for hunting. Be aware that the data set is huge. For stacking, the number of unique user agent strings across a typical production environment can be surprisingly large as well. So, to get the most value out of captured user agent strings, you have to filter out a lot to get to the actionable ones. Consider stacking the data by user agent string length rather than content, focusing on both the shortest strings and the longest strings in the data set. Also, analyze the counts of tokens or the word count in the strings, focusing on the lowest token counts. And lastly, of course, bump the entire data set against a list of known bad user agent strings. And please bear in mind that HTTPS blinds you to user agent strings unless you terminate that traffic and log it for analysis. A couple examples. Here we first have an example of what I mean by a highly unique low token count user agent string. See the HTTP browser /1.0 user agent string there? It has only one token and is highly unique in production traffic. If you see that HTTP browser string on your network, that is always APT and is always bad. Next, we have a user agent string that has a normal token count and normal overall length, which should never actually happen in production, so it would show up when stacking. This string, Mozilla 4.0 compatible MSIE 6.1 Windows NT, refers to a non-existent Internet Explorer version 6.1. This particular user agent string is only found in certain Metasploit traffic. In my experience, I've never seen an attacker use Metasploit for C2. I've only caught pen testers and red teamers using Metasploit for command and control. Next, Windows services are still commonly encountered in targeted intrusions and have been for years. In large production environments, you will likely find mining your services data productive. Let's explore a few ideas around that. There are a number of tools out there to dump out lists of installed services. Most of these tools have similar output and show almost everything you want to analyze for an installed service. Here we show output from Microsoft SysInternal's PS Service tool. Let's see what fields look useful for stacking and analysis. You want to look for rare, unusual, or typoed service registry names or display names. Those are the top two fields in the example shown. A commonly overlooked field when searching for malicious services is the service description. Some malware tries to hide in a crowd of similar-looking services by registry name, display name, and file name, but either typos the description field or leaves it blank altogether when the service it is trying to mimic normally has that filled out. The binary path name field is a good choice for hunting. You want to look for things running out of unusual file system locations, for example, highly unique paths or file names, or anything running out of temp. The example shown on screen is one form of what is known as service hijacking. In this case, the service was something that was already present on the machine, got its configuration changed to point to another malicious executable. For years, attackers have been repointing existing legitimate service configurations to a rogue binary on disk, hoping to escape notice. For legitimate system services, this type of problem shows up when stacking by the right fields. All of your healthy services will point to the right binary path name, or service DLO will point to something legitimate. If you have 10,000 services with the same name and display name, pointing to mostly all the same file path and file name, and then just one pointing to something different, that should stand out in your data. Now, over the years, Microsoft has regularly changed the names of the legitimate files on disk between OS versions and service pack levels. Despite that fact, one-off malicious service configurations like this one will show up when stacking. Hopefully now with Microsoft releasing fewer service packs on major OS versions, this will be less of a problem for us from a hunting and detection perspective. Most service analysis tools, including Microsoft's PS Service tool, don't report on one key field, and that is the service DLL value from the registry. The service DLL value for a service identifies what binary gets loaded when the service is configured to live inside of a shared service host container. I am not aware of a free and publicly available tool that can report the service DLL information. As a workaround, we can use Microsoft's List DLLs tool instead. The first command on screen lists all DLLs loaded inside of any service host.exe process. The second command shown lists only unsigned DLLs loaded inside of service host containers. This helps reduce the amount of data to analyze, but remember, some malware is digitally signed. Recall a bit earlier when we covered hunting for situations where legitimate service configurations in the Windows registry were altered to point to the wrong file on disk. This list DLL's approach helps you find the flip side of that hijacked service coin, situations where the service configuration in the registry is perfectly fine, but the file on disk has changed. Here we are playing off list DLLs-U to find unsigned DLLs loaded across all service host containers. The example on screen is showing where the legitimate Windows error reporting service still has its correct configuration, but its normally signed Microsoft DLL isn't the thing being loaded. The file name is correct, but the file isn't signed, and it should be, so that will require investigation. When you first start mining services data across a mature population of Windows machines, including servers, ones that have been around for years, you might see things like these unique service registry names and display names bubble out of your data. Service names using only GUIDs are easy to spot by searching for the curly brace characters. Garbage service names are often all lowercase for some reason. The command on screen can help you spot these across your data set. In my experience, most of these are commodity malware, even when found on servers, and are left over from days when SMB worms were more prevalent. But you have to investigate each to be sure. Next arrow. Similar to services, Windows drivers continue to be a commonly encountered component in targeted intrusions. We break out drivers here to highlight a couple additional things to look for. The commands on screen are an effective way to dump the driver list, with the best fields for hunting included. To dump all driver info, you can use Microsoft's driver query tool with the option shown in the first command. To dump the signed driver information, you can use driver query as shown in the second command. Here's some sample driver query output from a Windows 10 system. There are a number of useful fields here in CSV form that we will cover in a moment. What are some productive things to look for in the device driver's data set? First, the link date field shows when each reported driver was compiled and linked. If that field has been zeroed out or contains impossible or garbage timestamps, that is interesting. Intruders that time stomp their binaries and the NTFS MFT entries on the file system often do not touch the timestamp that shows up in this link date field. That lives inside the file itself. So if you find a driver with file system timestamps that are many months or years older than the file's link date, that could be interesting as well. Next, always examine the path to the binary image of a driver on disk, looking for drivers loaded from unusual locations on the file system, for example, any temp location. Does the driver file name itself have unusual characteristics, like the name is all numbers or hex digits? Look for rare and wrong-sounding driver descriptions like the one on screen, monitoring of hardwares and automatically updates to device drivers. Mind the display names, looking for the rarest ones in the data set and typos. You might be surprised at how many unique driver names exist across a population of servers, or even just a few thousand servers. Look for missing or unusual digital signatures on the driver binary. Eliminating signed drivers to reduce this data set is useful, but please be careful which certs you trust. Some hostile binaries are signed with stolen certs. Here's an example of a device driver that stands out as unique in the driver data set. From a stacking perspective, it is unusually noisy for three reasons. That key IP filter driver name is unique in the data set, as is the key IP traffic filter driver display name. So is the driver file name. Next arrow. AutoRun's data from all Windows machines is a productive place to mine as well. Microsoft SysInternal's AutoRuns is the go-to tool here, with its comprehensive coverage of most AutoRuns locations, all WMI AutoStart locations, and much more. This one is really easy to do. Just collect the data and analyze. It is about 250 to 500 KB per machine. The command on screen will collect everything the AutoRuns tool can find. AutoRuns covers most known AutoStart locations, but not all. For example, side-loaded DLLs and DLL search order issues will not show up in this data. Please be aware that you scoop up a lot of non-targeted commodity malware in this data set. Please be aware that the AutoRuns tool can now do virus total lookups as it scans, but I would recommend doing that at scale from your production machines. Do that centrally in a controlled way. Here too, you're looking for things running out of uncommon places, executables at the top of program data, the top of the recycle bin, app data, or out of any temp folder location. Reducing the data down to just unsigned entries, meaning entries where the string verified with a capital V isn't present, can help reduce the workload. Look for odd short file names like r.exe or 1.bat. Here we have 3 examples of malware from AutoRun's data. The first popped out of the data set due to the single character exe file name and the uniqueness of the launch starting field. The second and third one shows ways where the services and drivers information can stick out. And the second example, you've already seen that unique description before. And the third example, you never see a service named Microsoft Cache Service across a population of Windows machines. That entry also sticks out due to its not being digitally signed. Next, prefetch allows you to get an idea of when certain processes have ran from a different perspective than shim cache or AM cache. Prefetch is a system performance enhancement present and enabled on Windows client platforms from Windows XP forward, including Windows 10. All that we're doing here is taking advantage of another set of data that Windows already maintains. Prefetch is not enabled by default on Windows servers. Prefetch is disabled by default for most modern SSD drives, even on client platforms. Up to 128 files can be stored in Prefetch on XP and Windows 7. From Windows 8 forward, the limit increased to 1,024 entries. Prefetch is stored in system root/prefetch. The individual files themselves use a binary format, so you need a tool to parse them. Please be selective of which tool you use to dump prefetch data from your systems. Some approaches just look at NTFS MFT data for each entry in the prefetch folder. Try to favor tools that do that and have the capability to analyze inside of the binary file. One quick way to tell the difference is if you have a run count field in your prefetch output. There have been subtle changes in the prefetch file format between Windows versions over the years, so favor prefetch dumping tools that keep up with the latest Windows versions. Nursoft's WinPrefetch View tool is one that works. An example of its syntax is on screen. That syntax will dump the output in CSV file format. Let's take a look at what data is available. This is a single prefetch record as reported by Nursoft's WinPrefetch View tool ran from the command line with text-only output, not the CSV format. See that short hash string in red? That is a hash of the file that runs path on disk. For stacking purposes, please be aware that the hash value algorithm changes between some Windows versions. There are 3 useful timestamps: the created and modified timestamps for the file system and a timestamp that records when the process last ran. Those are all good for context. The process path is important to help find things running from odd places. The run counter field can help you tell what runs normally from what just ran just once. Now, malware can auto-start and have as high of a run count as legitimate software, but intruder actions like running credential dumpers and issuing recon commands might happen only once. What's the most productive way to approach the prefetch data set? Stack by the various fields we discovered and consider the timeline. Certain commands in sequence might be a problem. For example, credential dumpers, recon, scan tools, net ping, etc. ran closely together can be a sign of trouble. Watch for short names in the process exe field, especially if the run count is only 1 or very close to 1. Here's an example of an intrusion where we have unusually named prefetch entries in the data set from a single source machine clustered together closely in time, 7 minutes in this case. This was taken from the example that we covered earlier where the w32.exe, w64.exe, and dump.pwd binaries lived in C: users at the top of that folder. As is common across many intrusions from many actors, they have renamed common tools before use. Because they show up in prefetch, that is further proof they actually executed. Next, error number 9. How do trustworthy and reliable outside services that routinely inspect or crawl your internet-facing assets see you? What do I mean by that? One example. Google, as part of its normal internet-wide crawling activities, sometimes sees signs of malicious content on your internet-facing assets. Anyone can view the data by using Google Safe Browsing. In the example on screen, I asked Google Safe Browsing what it thought about the website LayerOne.org. It came back totally clean. Here's an example of a website that Google didn't consider clean. For sites that you own, if Google knows about a problem and makes that data available to you for free, why not mine that data? In my experience, Google Safe Browsing has a very low false positive rate. Now, when Google does find something wrong with a site, that doesn't mean that is a sign of targeted activity at all. But I think that it's still something you would want to know about. And it is a possible pinhole that could be used against you by a targeted actor. Any actor who might be constantly probing your perimeter looking for their chance to get inside. Google provides an API for doing this type of monitoring. Instructions are on the link on screen. Basically, you apply for a Google API key. It's free. That API key allows you to programmatically submit requests to safe browsing, including giving you the ability to bundle up to 500 lookups per request. Any sites that Google Safe Browsing think have an issue return with the string malware in the response body and HTTP status code 200. Otherwise, you get HTTP status code 204 and no data. Full details are on the links on screen. Here we show how to perform a scripted check of all of your websites through Google Safe Browsing. Do this only in compliance with Google's terms of service, of course. The first step is to take your entire domain list and construct the full URLs for wget using your API key. Next, we query Google Safe Browsing using wget. The 10-second wait guarantees that you cannot go over the current default limit of 10,000 lookups per day. The results will be written to disk, one file per check. If you check 1,000 domains, you get 1,000 disk files with results, one per domain. To find any problem URLs or domains reported back, you can search the files returned using the command shown on screen. If you like the idea of using one URL scanner, why not many? There are a number of effective URL multi-scanner services out there. A multi-scanner approach lets you take advantage of the strengths of a range of URL scanners all in one action. Now, I try to keep every recommendation in this talk restricted to things you can do for absolutely free, but most of the URL multi-scanners require payment of some sort for their API access. The most popular ones are normally very easy to use and have clear documentation to follow. Most work by issuing the requested URL or batch of URLs in a single post, and you get the data back in an easy-to-parse format like JSON. On screen, we have high-level steps for doing this. Just a couple of tips. Don't force a new scan on your first pass. Just read what might have already been saved over the years for each domain and URL that you have for every scanner supported. Most APIs for URL multi-scanners have a way to force a rescan. Do that next for all of your domains, strictly adhering to the service's terms of service and your API key limits. Next recommendation. Consider mining your NTFS file system MFT data across your Windows systems. One thing to look for there are entries that normally have empty extended attribute fields that now do have data in them. Extended attributes in NTFS are a way to store extra information or metadata about a file. Information that isn't normally part of the file system's bookkeeping. Most files on an NTFS file system don't have anything in the extended attribute fields. It is normal and acceptable to use extended attributes if need be, but unfortunately some high-end malware authors have adopted a technique where they might hide some hostile content in extended attributes as well. How can you find that type of activity? Here's one technique. First, you need to grab the raw MFT from each Windows endpoint. In the example on screen, we first show using HB Gary's fget tool to do that. The MFT is locked on running Windows systems. For newer Windows versions, fget doesn't work, so consider something like raw copy, as shown on screen with its download location. Next, chop the raw MFT into usable fields. In this example, we use analyzemft.py for that. The download link is on screen. This step provides us with a CSV file with the MFT parsed nicely into fields. Locate the EA and EA information columns in the CSV. Reduce the data to only include columns where either of those fields shown as true. Whitelist out what is normal in your environment to further reduce the data and analyze what's left. When you reduce the data this way, it goes from huge to a much smaller percentage. Things like Windows WinSXS and Windows CSE can normally be whitelisted. You will see patterns of normal across your machine population. Analyze what's left after whitelisting those out. If you do find something requiring further analysis, you will need to extract the contents of what the EA entry points to. Great work has already been done showing ways to do that. On screen are 2 links I'll recommend for full details. If you need to extract any data or contents from an EA entry, you would have to do that either on the source machine or from a full disk image taken from the source machine, because the data contents likely won't be resident in the MFT that you've captured. This isn't always high-end APT malware. It can be things like advanced cybercrime malware, but it is worth mining. Next, How might you go about knowing if a high-end adversary shoots a zero-day arrow at you and it sticks? One that has never been seen before, a true zero-day. This is one tough problem. This is more in the realm of a PhD-level attacker bringing their A game versus D to F game activity. Most of us have to depend on catching something later in the kill chain, but we can try to catch the exploit in some cases. EMET log mining might be one possible way forward. What's EMET? EMET stands for Microsoft's Enhanced Mitigation Experience Toolkit, and is a set of mitigations that you can add on to Windows to help add some additional armor plating against common exploitation techniques. It is most commonly deployed on Windows client platforms and works for protecting most everything except Java runtimes. EMET works on Windows servers too, from 2003 Server forward. EMET logs go into the Windows application event log. Basically, if EMET sees something is wrong, it takes whatever the prescribed action is and records that in the application event log. Not everything EMET logs is zero-day. You might encounter bugs or misbehaving applications that cause EMET log noise. However, you might be able to find use of zero days there looking at what EMET has blocked. If you see where EMET mitigated or killed iExport.exe or Office or your AV product and your machine is fully patched, that could be a bug or crash that looked like a problem to EMET, or it could be a thwarted exploitation attempt. You should know when this happens. Here's an example from July 2015 where a high-end APT actor was phishing using one of the Adobe Flash zero days leaked from the hacking team dump. If you rolled EMET out with the EAF mitigation enabled, then EMET blocked their exploit code upon execution. The blue text on screen is what EMET logged in this case. If you didn't find this phish attempt another way, this could have been your only chance to know an attack had been attempted. If you have rolled out EMET across your Windows client and or server population, EMET log mining should be an effective zero-day detection method for you. Next, our 12th and final arrow. Consider proactively pulling back Windows RAM dumps from select systems and processing them. Maybe it is too much to attempt all of your systems due to the amount of data being collected being multiple gigabytes per machine. Maybe focus more on pulling RAM dumps back from key systems, internet-facing systems, or ones that you're most worried about for one reason or another. For example, interesting machines from new company acquisitions. RAM dumps have many more nooks and crannies in which to look for anomalies and signs of intrusion, but it is a huge amount of data. The good news is that you can script RAM dump analysis to an extent with tools like the Volatility Framework. First step, how do you get the RAM dumps? There are a variety of tools available. Most work similarly, and many are free. However, almost no RAM dump tools collect everything. For example, video RAM and device memory ranges. Try to select RAM dumping tools that can reliably and safely collect everywhere that malware can hide. George Garner's KNT tools is an option. Hardware dumpers are another option, but they're a bit more costly and intrusive. There are tons of useful data to mine of these RAM dumps. We will just highlight just one special case here. What are you doing to find BIOS or firmware implants across your server and client hardware population? This is another tough problem. Whether we are talking about system board BIOS or firmware in hard drives or supporting networks or graphics hardware, we are currently at a pretty lopsided disadvantage as responders and defenders. Implants in BIOS or firmware typically leave little to no detectable trace. But we need to do the best the current state of the art allows us to do, right? For example, the Art of Memory Forensics book, citation and authors listed on screen, has some interesting suggestions for detecting certain types of BIOS and firmware implants. One suggestion is to check the real mode interrupt vector table for signs of tampering. Another is to check the uppermost addresses in real mode memory for any traces of an implant. What's on screen was taken from a dump of physical RAM from a 32-bit Windows 7 machine. Using the same technique on a 64-bit Windows 7 machine works as well. The real mode interrupt vector table normally starts at offset 0 in physical memory and runs for 1024 bytes. You can tell if you're on the right track if you see repeating 4-byte sequences in the dump. Those are pointers to interrupt handlers. The first 4 bytes store the handler for interrupt 0, the next 4 bytes for interrupt 1, and so forth. This command shows syntax to generate a more structured dump of that same real mode interrupt vector table in a format easier for data stacking and analysis. That command will list all 256 interrupts on the table with the address of the associated interrupt handler. The address is starting with F00, F000 point inside a standard BIOS. The C000 normally points inside a video BIOS. You're looking for what is normal here, what could have been tampered with or hooked by an implant. The second suggestion from the authors of the volatility book was to inspect the uppermost addresses in real mode memory for any traces of an implant. Here I suggest you deviate a bit. If you have indicators, strings and byte sequences that can detect a particular BIOS or firmware implant, then I believe that it's better to scan your entire RAM dump, including what you captured from real mode memory. That sounds more thorough to me in case any indicators leaked outside of real mode memory and based on how the implant operates. Also, it is better to search the entire physical dump file as a binary blob, in addition to structured searches using tools like volatility that may be checking only process address space or kernel space depending on the circumstances. So, doing your structured searches in volatility with its Yara support is effective for this purpose, as the examples on screen demonstrate. But also search the whole RAM dump for the same indicators to make sure you cover the entire physical address space. A third suggestion from the volatility book for hunting for implants is to see if something called the I/O APIC indirect access registers have been tampered with to reroute interrupts. APICs and I/O APICs are pieces of hardware used to support the processing of interrupts on multi-processor systems. I don't have a scripted volatility command ready for this one yet, so I will instead show you the manual steps to get to this data using the Windows kernel debugger. This output on screen is from a 32-bit Windows 10 machine. The process goes like this. You either have to convert your RAM dump to Windows crash dump format or collect it in Windows crash dump format to begin with. Then open the crash dump file in the debugger. In this case, I'm using the command line KD debugger, but WinDBG works just as well. I issued a .logopen command to save the contents of the session to preserve the IOAPIC command output. And lastly, you type bang IOAPIC to dump the IOAPIC data out for later comparison and analysis. The idea being to look for deviations from normal in this data set, for example, where an implant may have repointed one of these addresses for its own purposes. Lastly, a few closing thoughts. First, get the noise out of your environment. Intrusion hunting is difficult and tedious enough already, so whatever you can do to avoid spending time on commodity malware helps. Toward this end, deploying Microsoft EMET helps. Patching, on the client side, mainly the operating system, Microsoft Office plus Adobe Flash Player helps for sure. At a minimum, across all platforms, meticulously patch anything known to be remotely exploitable. There is another helpful thing that you can do that might not be so obvious, automating malicious email cleanup. Some of your spam and phish protection vendors have a feature where if you have an inbound phish affecting, for example, 1,000 mailboxes, and that vendor lets in say 100 before it realizes it is malicious and started blocking the remaining 900, you still have 100 potential problems in people's mailboxes in production. Some vendors provide an API that you can use to see what slipped in. The idea here is to take that list of 100 phish that leaked in and trigger auto removals, deleting the phish email from users' mailboxes automatically, hopefully before anyone gets a chance to be tricked and click. For those with Exchange environments, Microsoft has an easy-to-use API for this, whether you're using on-premises Exchange or cloud-hosted Exchange. Doing this should help reduce the noise that you have to deal with when hunting for more serious intrusions, even in the most secure networks. Okay, next thought. After working any new intrusion in post-mortem, think carefully about exactly what could have alerted you to that intrusion earlier, as well as along as every step of the intruder's path. Add that to your hunting process as required. Go back through your entire case history, all historic intrusions, and do the same. What could have found the intrusion earlier or more reliably? When you read about intrusions affecting others in vendor reports or in the news, mentally do the same. Could your organization have found that intrusion earlier on your own? Be consistent. Convert as much of your manual intrusion hunting processes to automated detection as you can. Managers, please fund your hunt functions. And don't back off just because the volume of detected intrusions might be low for an extended period of time. It's tougher out there now. I'd like to thank you for your time. I'd like to open up now for any questions. Thank you. If you have a question and you don't want to broadcast in front of the group here, I'll be loitering out here for a while until no one needs me anymore. So see you outside. Thank you very much.
When you're talking about firmware injections, you're talking about malware injection, getting into the firmware, into BIOS?
No, that's a firmware, whether it's on the system board itself or in devices. Plug in cards, hard drives.
Yeah.